Welcome to ACHR. Let me talk about a little bit about me as a starter. I'm Michael. I'm running the Powertrain team here at ACHR. A little bit about my background. I spent a couple of decades in the traditional automotive industry and then joined a small startup located in Palo Alto at Deer Creek Road. Back then, we produced 30,000 cars a year. Now I think they are up to like roughly 1 million. So I ran the Powertrain team at Tesla, not only for design engineering, but also for manufacturing engineering. In my tenure over there, we did the drive units for Model 3, Model Y. We overhauled Model S and X drive units, laid the groundwork for Roadster 2 and the semi-truck which will be launched later this year. The importance back then for me was always the strong connection between the design and the manufacturing portion of it. We built some pretty leading edge assembly lines and manufacturing lines for a few $100 million over there. My team was never in production hell, but obviously we had to help out when others were. So that was a really amazing experience that taught me a lot for the stuff that is to come here, but also the stuff that I have been working on since then. After Tesla, I worked in Apple Special Projects for almost 3 years. I really can't talk about what we worked on, but it was very, very interesting, as you can imagine. And then I decided it's time to do something new, and I decided to join ACHR. And one of the reasons why I decided to join ACHR is the bullet points that you see on the next slide. At ACHR, we have something that we call realistic innovation. And let me elaborate a little bit on that. When you look into Silicon Valley, there is a lot of leading edge, next generation innovation. Everything is questioned, everything is turned upside down, and we develop a lot of stuff. But there is typically 2 items that Silicon Valley companies struggle with a little bit. And one is obviously to focus on the stuff that really makes a difference. At ACHR, we focus our innovation on the stuff that makes a difference for our customer and a difference for our product. We don't think there is a point in developing new tires for an eVTOL aircraft. There is other companies out there. Our supply base, we have like world-class suppliers that can help us in many, many areas that support us. Why would we go and try to reinvent the wheel in this case, just for the sake of reinventing the wheel? We really want to focus on the stuff that will make a difference. And the stuff that will make a difference, obviously, in an eVTOL application is the electrified powertrain. Because that's the thing that is different between traditional aircrafts and eVTOLs. The second item that Silicon Valley companies typically struggle with a little bit is you have to get it done 100% before you launch. I mean, just remember your last smartphone. How long did it take until you got a software update? A week, 2 weeks? Obviously, when you're talking about aviation, you cannot do that. 1, it would be the wrong thing to do. And 2, obviously, the FAA won't let you launch a product and then say, well, we will fix it in the field later on, right? That's not a thing that will fly with them. So these 2 topics were really attractive for me when I decided to join ACHR. And there were a couple of other topics that we are optimizing our system design for. And first and foremost, it's safety. This airplane has to be safe. There is no other way to do it. I want to fly in it. I want my family to fly in it. So we can't cut any corners, and safety is front and center in this company, and that was really, really attractive to me. Next one is efficiency. Every single watt of energy that we waste because we are not 100% or close to 100% efficient has to be stored in the battery pack, has to be charged into the battery pack, has to be paid for from the grid. So it is ultimately important to have a very, very efficient aircraft and also a very, very efficient powertrain. Which brings me to the next point, power density. And maybe you can easily call it lightweight. the powertrain itself has to be as lightweight as possible, but still do the job, because you want payload. We have an aircraft that has more than 1,000 pounds of payload, and we want to maintain it this way. Just imagine we would waste another 200 or 300 pounds on the powertrain and had a payload of 600 or 700 pounds. We wouldn't have a product, because we want to fly 4 passengers in our airplane. And we don't want to end up with a glorified school bus. We want to end up with a product that can transport 4 grown-ups and the pilot. The last one is commercialization. What drives me typically is seeing my product out in the wild. I'm not a researcher in terms of spending a lot of time at Stanford or at one of the universities that I've seen in my career. I really get excited when I can ship a product. And ACHR has a very, very clear commercialization strategy, a very clear strategy of designing a product that is safe and going to market in the shortest amount of time possible. And those typically really important points were super important to me, and also one of the driving factors that made me decide to join ACHR. So how do we make all of this happen? It's very easy how to make it happen. It's very difficult to do it. To make this happen is you need a world-class team. And when I say world-class team, I mean really, really, really good engineers that I have worked with in my past careers, that have slept on the Gigafactory floor in Nevada when the shit hit the fan. Sorry for the rough words. But that really can plow through it even if times get rough. That is really important, that you have a leadership team and a team that you can rely on and that will get the job done. And when you look into the team that we have assembled, we basically hired from all over the place. We are not religious about it has to be Silicon Valley, it has to be traditional automotive, it has to be traditional aviation. We are religious about hiring the best people. We have people from Apple, from NASA, from some of our competitors, from Tesla, obviously. We have people from GM, from Bloom Energy, not only our CFO. And we have assembled a team that has more than 200 years of experience just in the leadership team of powertrain experience. And when I say powertrain experience, I mean products that ship. I don't mean products that could maybe exist at some point in time. The total team that is working on powertrain is roughly 100 employees. That's also supporting functions, obviously. But that gives you a glimpse into what we focus on, but also what we put our efforts into, and that is obviously one of the halo things that we have to build and have to deliver. And before we go into a little bit of better understanding of 2 of the most important systems in the powertrain, you will see some pictures in the presentation later on. Some of the pictures have hidden stuff that we don't want to disclose as of now. Just because you see a picture of a cutaway model, it doesn't mean that all the bits and pieces are in there. So bear with us, but we need to keep a little bit of the secret sauce and not give it all away. We feel we have pretty well protected us with IP before this presentation, obviously. But some of the stuff is still in the making, and some of the stuff is just not 100% ready to be filed. That's why we couldn't show it to you. So just because you see something or don't see something, it doesn't mean it's actually not there. With that, I want to turn it over to Alex Larwood. Alex is my head of battery development, and we worked together at Apple for a couple of years. And he will talk you a little bit through the design of our battery pack. Alex.
Thank you. Thanks, Michael. My name's Alex Clarabut. I'm the Director of Battery Systems here at ACHR. Prior to coming to ACHR, I worked for 6 years at Apple on Special Projects Group. I managed a battery team there. And before that, I started my career in solid oxide fuel cells, working on stationary power generation. And And if you go way back, I developed my first battery systems in middle school for a worldwide competition. So I've got a long and varied past in developing systems for power, efficiency, and energy. So why did I come to Archer? First of all, I'm a pilot. I actually got my pilot's license just across the street a couple of years ago. So I love aviation. And then also, I love batteries. So electric aviation is a pretty good spot for me. But I'm also a battery skeptic. And before Archer, I didn't really see any companies out there that were doing anything with realistic innovation like Michael talked about. What we're going to talk about today is something that we can produce today. So that really excited me when I met the team here. So I'm going to talk to you about our high voltage power system. But before that, I want to reiterate what Michael said about the team. The battery system team has about 30 engineers directly working on the battery. They come from places like NASA, Apple, SpaceX, Tesla. And we really hired a group of people that's got experience taking high performance batteries into production. And I'm excited to talk to you about what the team's come up with for Midnight. First of all, before we get into the details, like why do we need a battery? Basically, we're taking traditional aircraft, that's energy source is jet fuel or aviation fuel, and we're replacing it with lithium-ion battery cells. Lithium-ion batteries are great. One of the nice things about them is they can use sustainable energy to recharge, but the downside is they're heavy. And so the group and the team here has to do really great optimization around minimizing mass of the battery so our plane can fly. So where does that start? It's basically this plot right here on the right-hand side. We've got a set of Archer requirements, but this basically outlines the performance requirements for the battery. And I'll talk you through them from left to right. So power, electrical power on the y-axis, time on the x-axis, and this is basically an example of our longest range trip. So it's about 50 to 60 miles. And so for the battery, what's important are these peaks here. And I'll talk you through them. So first of all, the plane takes off. It's a vertical takeoff. We're hovering a 6,500-pound aircraft. It takes a lot of power. Just to contextualize this, it's about 1,000 horsepower to hover. 1,000 horsepower is, equivalent to a Formula One race car, a significant amount. So then we transition to climb, cruise, descend, and we have another high-power landing down there. So this is normally our longest range trip. But we also have to account for heading to an alternate airport. So the dotted line shows this alternate mission. We immediately have another high-power takeoff, climb, cruise, descend, and then another high-power landing. Important part here is we design it so we can have a landing with an equipment failure at the worst part in time. So what that means is the battery can fail, the engine can fail, and we can still land safely. The downside for the battery is that takes a lot more power. So that really high peak right there on the right-hand side is the sizing case for us. If you're familiar with lithium-ion batteries, they don't like that. They like to provide power on the left-hand side of this plot at the highest state of charge, and then they can provide less power as you lower the state of charge. So that's really important for us, and that's really what sizes our battery pack here. So these are our performance requirements, but it's just a subset of all of our requirements. So on the left-hand side here, we really think about safety, certifiability, and then performance requirements, and then we go down to commercialization. And I'll talk you through those. After we have our set of requirements, what do we do from there? We have to figure out what the plane high voltage architecture is. Basically, how do we decide our architecture? We had, weeks, months worth of debate on this. And what was in focus for us was safety and commercialization. So we came up with something pretty cool and proprietary. We have 6 batteries. Each battery pack supports 2 motors. The battery packs are at 800 volts. But there's connections between the batteries that allow them to intelligently shuttle energy back and forth. So this is important in case of a battery pack failure. Another battery pack can take over. But it also allows you to isolate the batteries from each other. So again, if there's something that happens on one battery or one engine, other batteries and engines can take over. So, two key things on this. It's obviously safe, it's fault tolerant to potential failures, but it also enables us to reduce the power requirements at the battery cell level by 20% compared to a standard high voltage architecture. So 20% is significant. If we had to add 20% of mass of battery cells back into this, it'd impact our payload by about 300 pounds. So this architecture is a huge enabler for us. The other thing about this is when you reduce power, you get a bigger catalog of battery cells to choose from. Ultra high power battery cells are kind of a niche market, but as you reduce power requirements, you get more and more cells available to you. So we've got our architecture, now we choose the battery cell. And the battery cell is critical. It's the building block of the entire battery system. There's anywhere from 100 battery cells to thousands of battery cells in a high voltage battery pack. And basically, it's the only thing in the battery pack that's storing energy, providing power. So it's, obviously key to making this aircraft fly. So when we think about selecting a cell, we don't really care about what the cell can do by itself. We really focus on what the cell can do in the context of the battery pack, battery system, and in the aircraft. So again, we come back to safety and commercialization. There's 3 cell form factors that are commonly available. There's cylindrical cell, prismatic cell, pouch cell. We chose a cylindrical cell for a couple reasons, starting with safety. So a pouch cell is probably the highest energy density and power density cell on the market. Problem is, there's not a dedicated safe architecture. So a pouch cell doesn't have a cell vent. And the FAA, when we go to certify this battery pack, we have to force a cell into thermal runaway in the battery pack and make sure the battery pack responds safely. So thermal runaway is when hot gas flames come out of a battery cell. It's hard to do. So with a pouch cell, without a dedicated safe architecture, it's even harder to do. And so even though it's maybe higher energy density or power density at the cell level, you may have to give up that mass when you go and design your battery pack to make sure this is safe. So we throw pouch cell out the window. We've got cylindrical cells and prismatic cells left. The next thing about safety, going back to thermal runaway, the lower the energy of the cell, the lower the energy of the thermal event. And so cylindrical cells, they're pretty good energy density and power density at small energy levels of the cell. Prismatic cells are not. So we went with a cylindrical cell. It's got a proven safe architecture, demonstrated reliability, decades of volume manufacturing. In fact, Tesla shipped about 4 billion cells, 2170 cylindrical cells, last year in the Model 3 and Model Y. So it comes with favorable economics and a significant supply base as well. And we're not counting on a technology breakthrough. We're not going with a fancy custom cell that's not going to be available in 2027. It's available today. In the last 48 hours, we've signed an MOU with Molicel. Molicel, or E1 Moly Energy, is one of the original lithium battery developers. It's actually founded in 1977 in Canada. So Molicel's famous for delivering power cells. They've developed EV cells for BMW, Zero, among others, and they've got a gigafactory coming online in Taiwan in 2023. So we're really excited about this. We've been testing Molicel cells for tens of thousands of hours in our Archer-specific mission, just like we showed on the plot, and it's capable of over 10,000 plus missions, 10,000 plus average missions of 20 miles. Okay, so we've got our battery cell. What do we do with it? We have to design the battery pack. This is up here is our battery pack for Midnight. Like Michael said, this cutaway is awesome looking. It gets you a glimpse of inside, but it's missing some things. We're trying to save some secrets for later. What do we think about when we're designing this battery pack? Again, back to safety. FAA has some pretty stringent requirements, as they should, on designing a battery pack. We have to meet DO311A. It's forcing cells into thermal runaway, making sure the pack responds safely. So we've done hundreds of tests at the cell level and the prototype level to ensure that we meet that standard. and we've come up with something pretty cool. We've got a proprietary thermal runaway strategy, and it works great. So, other things on safety besides thermal runaway. On top here, we have our battery management system. Just like our battery pack, if we have a failure with that or a failure with an engine, and we can respond safely, if we have a failure with the battery management system, we've got enough redundancy in the system to be able to continue to fly safely. So those are the safety critical items on the battery pack, but it's also high performance. We talked about how critical it was to reduce mass. We've got engineers with experience in high performance composites and materials to ensure that we minimize the mass, increase the payload of the aircraft. The other thing about this battery cell and this battery pack design, when we have to meet that really high power requirement for discharge, we kind of get for free great charge performance. And so what we've shown is that we can do 10-minute recharge for our 20-mile average mission. And it's not just once, it's over and over and over. So the other goal for the battery pack team is not to make one of these. We need to make thousands of these. So ingrained within the battery design team is manufacturing engineers, tons of experience in producing batteries, and we've basically implemented their feedback from day one of the design. So we're working with our manufacturing engineers to make sure that we can make thousands of these. So what are the key takeaways here? We have a safe, fault-tolerant design for our power system. It really, not only is it great for our customer, but it minimizes speed bumps with the FAA. It's high performance, low mass. It supports our high payload in the aircraft. It's got a great turnaround time of about 10 minutes for a 20-mile mission. And we've shown over 10,000 plus cycles on this battery when performing our 20-mile mission back-to-back, while maintaining some life after we take out the battery from the aircraft for second life applications. So that's our power system. I'll hand you over to Alan to talk about the electric engine.
All right, thanks, Alex. So my name is Alan Teepee, and I lead the inverter design team here at Archer. Before joining Archer, I worked at Tesla for 8 years as a design engineer on the inverter team there as well. And for 3 years, I led the inverter mechanical design team at Tesla. I really enjoyed working at Tesla. It was just an awesome experience. All the engineers were incredibly talented and very driven. And while I was there, we went through 4 iterations of drive unit design. So that's basically the motor that propels the vehicle. And with each iteration, we focused on the engineering fundamentals of what makes the design work and really focused on simplifying the design down. And that was a big part of what enabled Tesla to scale up in production as well, because the designs got higher performance and then they got simpler with each iteration too, so they became easier to build. So at Tesla, electric propulsion really revolutionized transportation on the road. And when I learned about Archer and what they were doing with aviation, I just really wanted to be part of it too. I really think that electric propulsion is going to revolutionize aviation as well. So today I'm going to talk about the electric engine design. Before I get into that, I wanted to talk a little bit about just electric motors in general. They're really incredibly simple at their core. So an electric motor typically consists of it's a rotor on the inside, and you can think of the rotor as basically just a round magnet. And then on the outside, you have a ring of electromagnets that we call the stator, and that is really just a segmented magnet that you can turn on or off using a switch, and the switch is really the inverter, kind of the driving system for it. So really how it works is you just turn on those electromagnets on the outside in a circular pattern, and that produces torque between the 2 sets of magnets, and that drives the output. So it's fundamentally really simple. It's really magnets chasing magnets. It's drastically simpler than an internal combustion engine, where you have fuel that's being pumped in. You have to ignite the fuel. You have to have the right air fuel mixture to be efficient. And it's explosions that are driving pistons, and it drives like a shaft that does the output. It's just very simple components here. So when I joined Archer, our team of 20 design engineers was tasked to design the electric engines. And the key design requirements for this were that we needed to hover the aircraft, so lift off from the ground and hover, and then transition to cruise flight. And the most challenging part, really the sizing case for the engines, is that hover portion. So there, all the weight of the aircraft is supported by the thrust of the engines, whereas in cruise, the weight is supported by the wing. So really the engines are sized for that thrust case. Some of the constraints or challenges with this is that in order to have a low noise profile, we want to spin the propeller at a low speed, but a very high torque. So we want to limit the speed of the propellers such that they're not too loud and they cause noise for the passengers or people on the ground. We also need to minimize the weight, so we want to maximize the aircraft payload, and most importantly, safety. So we need to make sure the aircraft has a high standard of safety and no single point failures. So with these constraints, the first big decision we made was deciding on the number of engines. And one of the big drivers here is you have to make sure that the thrust on all sides of the aircraft is equal in hover. Because we wanted to make sure we had no single point failures. And as you can imagine, if you only have like 4 propellers and you lose one of the corners, you can't really balance out the load with the other 3 propellers. So we looked at a ton of different options for this, and we decided on 12 propellers overall. So 6 tilters in the front that tilt forward and power it in cruise flight, and then 6 lifters in the back that are only used in that high power portion in the beginning when you're hovering off. And this was a big decision because it gave us a high level of redundancy. So we have redundancy at the propeller and the engine level. So you can lose propellers on opposite sides and still keep yourself balanced and maintain hover. So that's really important for our overall strategy. So once we had selected the number of propellers, that gave us basically the detailed thrust requirements for each propeller, and we were able to start the detailed design of the engine. So here we had the team of 20 design engineers. We spent months going over every different conceivable design option and brainstorming on whiteboards, coming up with everything we could do to simplify the design. And at the end, we came up with this engine design. So we have a sample right here. So I'm really proud of all the work that we did on this, and it's a great design overall. So it's very safe. So we were able to add additional redundancy levels inside of the engine in addition to the overall engine redundancy. It's also very simple. So we're using mature technology that's already used in other products or it's out in the field. So for example, like in the inverter, we're not using components that are brand new and haven't been tested in the field yet. We're using components where we have a good track record of field performance to make sure we're not learning things on our first builds that we shouldn't be. And I think also very importantly, it's very lightweight. So using this engine, we were able to help achieve our 1,000-pound plus payload at the aircraft level. Another thing we're able to do is maintain design commonalities between the tilter and the lifter. So we have about 95% of the same parts between them. Really, it's just the 2 outer housings that are different, outer housings in the output shaft that are different. And this is important for basically scaling up our manufacturing operations. So we can effectively have the same line that's producing both sets of engines, and then we just put the different housings on at the end. And it was maybe a slight compromise in overall performance, like if we had separate engines, we could have maybe slightly better weight overall, but this was really important for scalability. As I said before, we were able to build in some redundancies inside the engine. So for very little mass penalty, we were able to add in a dual wound motor and a dual inverter. And for mini failure modes, if one of those sides fails, you can just use the other side to continue outputting torque to the propeller and keep flying on your mission. So it's similar or electrically similar to having actually 24 engines in the aircraft. So it's really a pretty big step in extra redundancy. So one way to highlight how simple our engine is to compare it to an internal combustion engine. So here I have a comparison between our engine and the engine that's in a typical Cessna 172 aircraft, which is one of the most common aircraft in the world. So in the Cessna 172, you have 10 gallons an hour of fuel coming in. You're igniting that fuel, making explosions that are really loud, and driving pistons that basically push the propeller. And in doing that, you're generating a ton of waste energy. So 330 kilowatts of waste energy coming out. That's really enough energy to heat 14 houses. So it's a massive waste of energy there with internal combustion. You've got a bunch of emissions, so like 90 kilograms an hour of CO2. And the most common aviation fuel actually still has lead in it. So there's also 20 grams of lead coming out the back as well. And additionally, there's a ton of moving parts. So all those components are moving around. There's lots more wear mechanisms in the design. So you have about 160 moving parts in the Cessna engine. And we can contrast this to our engine, which have a similar peak power level. And here you just have HV power coming in, 132 kilowatts, and you're just basically creating those magnetic fields to produce the torque at the output. And you have 7 moving parts overall. So much less waste heat. It's very efficient. It's also drastically lighter, so it's about 5 times lighter for the same power output. So this is really the thing that helps to overcome the present technology of lithium-ion batteries. We're saving a ton of weight on the engines. So it's 5 times lighter, 21 times fewer moving parts, 50 times less wasted energy overall, and there's 4 times lower energy costs if you multiply out the cost of gas and the cost of basically charging off the grid. So one of the biggest decisions we made in our design is we decided to add a gearbox to the motor. And this was based on a huge amount of work by the electromagnetics team looking at all the different design options. And basically what we found in our design trade-offs was if you connect the motor directly to the propeller, it's not very efficient in terms of how much power out you get versus the weight of the motor, because it's a very high torque motor and a very low speed. And to get a higher power density, you really want to spin faster and kind of have a slightly lower torque overall. So we did a huge number of trade-off studies and basically found that if we could reduce the size of the motor by spinning it much faster and then using a gearbox to trade that speed for torque at the output shaft. So this is shown here. It shows that on the left, we have our direct drive optimized design, and it's this huge pancake motor that connects directly to the output propeller. And on the right, we have the design that was optimized using a gearbox. And you could see we shrunk the motor down to almost half the size, and it was just a huge reduction in mass. So the motor is about half the size. Overall, this allowed us to increase the aircraft payload by more than 100 pounds. And it also has big benefits in terms of manufacturability. So with the big pancake motor, it's outside the realm of most motor manufacturing processes. But adding the gearbox and shrinking down the motor gets us back in the realm of typical automotive motors. And so it really opens up the supply base. So it's really a big decision, but we really think this was the right direction to go. I also want to add too, it's a relatively simple gearbox. So it's a small gearbox about this big, and we have a great team to execute on the gearbox. So the team has about 70 years of experience with gearbox design, and they've designed and shipped into production multiple gearboxes that are designed for million-mile plus operation. So overall, our design that we achieved is very lightweight, and I put this together just to kind of highlight how it compares to other high-performance motor designs. So for example, we have the Model 3 drive unit over here, and I also have shown a motor that was optimized for traditional takeoff and landing aircraft. And they're not bad designs by any means. They're really just optimized for their application. But you can see that the Model 3 drive unit, it weighs about 4 times as much as our motor, but the output power is less than double ours. So we have more than double the power output per unit mass. And the other aviation motor, it's not quite the same, but we have a higher power output per mass for that design as well. And really, this just highlights how critical it was for us to optimize and create a custom motor design for our aircraft. And in doing this, if we just started out and said, oh, we're just going to use these other high-performance motors that exist, if we had taken those motors and put them on the aircraft, the overall propulsion system would weigh about 500 pounds heavier than it does now. So really it just shows the benefit and the need to optimize the motor for a particular application, which we've done, and I think the design we've achieved is really great in terms of mass. So overall, I wanted to thank the team. There's again, a team of 20 engineers that did a ton of great work on this, and I'm really proud to have been part of it. Our design is really safe with its multiple redundancy levels. It's very simple, so we're using mature technology that's ready for mass production. And again, it's super lightweight, so our design was a big part of achieving that 1,000-pound payload. So thanks for your time, and I'll hand it back to Michael.
Thank you, Alan. Let's summarize. To reiterate, our prototype battery management system. You will have time to have a look at this. The electric engine that we designed with the inverter, the gearbox, and the motor inside. So this is it. This is all. There is no additional boxes or something like this attached to it. And so What I want you really to take home, and we're not ending this presentation, but take home from the powertrain area, is a few key things. One is our strong belief in a realistic innovation. Focus on the things that make a difference for the product or for the customer in-house. Leverage our supply chain and supply bases for all the other things that have to come together to build a great aircraft. You've seen some of the announcements in the recent days around Garmin, around Molicel. It is a very focused approach on innovate in the areas that make a difference on the product side and get it done in time. That's what it really is. We talked about the battery, optimized for safety, obviously, really, really important. As Alex told you, you have to be thermal runaway tolerant. The FAA enforces you to bring certain battery cells in your battery pack into thermal runaway, and you have to show them that you don't end up with a problematic situation. And also prevent propagation, because you have a lot of battery cells in here, and you have to have a design that even if one cell goes off, the other cells around it don't do the same. We need longevity. We are performing on a level of 10,000 average missions per battery pack set. We also need short recharge times, 10 minutes recharge time for the average mission. And this is combined with a high efficient electric engine. One, the efficiency of the electric engine enables a smaller battery pack size, obviously, because you don't have to utilize the energy that you waste then in inefficiency, but also it reduces the charge times. Alan talked to you about the gearbox design, which enables higher power density, which then enables higher payload. And it's really, really important to us that we are using known building blocks. And that enables us a safe and also achievable development cycle. Last but not least, I can't stress it enough, we have a world-class team. We think by far the best powertrain team in the industry. I've worked in my prior lives with most of them. I have seen what this team can do. I'm still seeing it every day. And we will get this in time, in quality, and convince the FAA